Hi everyone. So we're going to be continuing on with the series of radicals, but today I'm going to be teaching you guys how to apply cube roots instead of square roots. So I mentioned this in our first radical video, but the radicals that we've been working with up till now have all been square roots. So today we're going to be moving on to something a little bit more new. So square roots we worked with perfect squares and taking them out of the radical, and cube roots is kind of what it sounds like. You take out cube roots out of the radical. So square roots, I mentioned this before too, that when you just write a plain radical with no number in the index, you automatically assume that's a square root, just like how you assume a base of 10 for a log with no base written in it. So this is a square root, but if you write a number in the index, it turns into something else. So this would be a cube root. But a square root also, you can also write a 2. No one really does that because it's already implied. So since now we know what a cube root looks like, I'm going to go over the perfect cubes, just how we went over perfect squares for square roots. So starting off with the basics, we're going to go from the smallest cube root to the smallest perfect cube to the biggest perfect cube. So from 1 to 10. So starting with 1, 1 cubed is equal to 1, because anything times 1 is equal to 1. And then 2 to the third power is 3 to the third power is 27. 4 to the third power is 64. 5 to the third power is 125. 6 to the third power is 216. 7 to the third power is 343. 8 to the third power is 512. And as you can tell, the numbers are growing really fast because you're multiplying the number 3 times instead of 2. And then 9 to the third power is equal to 729. And finally, 10 to the third power is 1000. So it's okay if you don't have the bigger numbers memorized at the top of your head, but you should at least know, I would say, 1 through 5, and have them memorized so that you don't need to think about doing the math in your head. So these are the basic cube roots we're going to be working with today. Now I'm going to give you a basic example problem just to grasp the concept of how cube roots work. So our first one is going to be the cube root of 64. So just as we did square roots, we're going to be looking for perfect cubes inside of this radical. So just like how we went over, 4 times 4 times 4. So we see that 4 is multiplied 3 times, therefore we can take it out of the radical and just have it equal to 4. So the cube root of 64 is equal to 4. Let's try another one, the cube root of 27. So if we break down 27, the first thing you probably think of is 3. And we don't see any numbers repeated 3 times here, so we're going to break it down even further, because it's equal to 9 times 9. And so, 3 times 3, so we have 3 times 3 times 3. So 3 is repeated 3 times, which makes it available to be taken out of the radical. So the cube root of 27 is equal to 3. And so these are all perfect cubes, and you should probably try to have them memorized. Next, we're going to do the cube root of negative 125. Now, you might notice something different about this one right off the bat, that it has a negative sign inside the radical. Now, what makes this so interesting is that when we did square roots, because that's another thing you'll learn in the future when you do harder math beyond pre-algebra, but we're not going to go over that because I'm trying to focus just on pre-algebra for now. But you can't have a negative number, you can't have a negative inside of a square root, because if you think about it, nothing squared can be negative. If we multiply two numbers that are negative, it's always going to be positive, so you can't have a square root of a negative number. Cube roots, on the other hand, you can have a negative, because if you think about it, you can cube a number that is negative and still end up with a negative, because if you don't have the right amount of negatives to cancel each other out, you're still left with the negative. So in the end, cube roots, negatives can work. An easy way I remember it is that if the index, which is this number right here, is an odd number, you can have a negative, but if it's an even number, you can't have a negative unless you're working with more complex numbers, which you don't have to worry about for now. So, like always, we're going to break this down. So, negative 125 is negative 5 times negative 5 times negative 5. Now, the reason why I'm putting negative 5 for all three of the factors is because cube root implies that there's a number that you multiply 3 times, and so if you have two negative 5s and one positive 5, that's going to cancel out, so it doesn't work. If you only have one negative 5, it does work, but it's technically not the same three numbers, so we know that it's negative 5 3 times. So we're going to simplify this down. So because there's three negative 5s, we know that it can be taken out of the cube root, and so our answer is negative 5. Now let's work with some cube roots that aren't necessarily perfect cubes, but have perfect cubes within the factors. So the cube root of 40. So from our basic times table, we know that 40 is 8 times 5. And 5 is the prime number, so it can't be broken down even more, but 8, is 4 times 2. And we still aren't seeing three of the same numbers, so we're going to break down 4 even more, because 2 is broken down all the way. So I'm going to take this up here. 4 is 2 times 2, and then we have times 2 times 5 from the rest of the factors. So if you look inside of the radical, we see 2 is repeated 3 times, which means it can be taken out of the cube root. So we're left with 2 times radical 5. And that's our final answer. Our next problem is going to be the cube root of 80. So 80 is 8 times 10. And from the previous problem, we know that 8 is equivalent to 2 cubed. And so we can take out the 2, and we get 2 times the cube root of 10. And if you just think about it inside your head, 10 is 2 times 5, which are both prime factors, and we don't see any numbers repeating 3 times. So this process will go a lot quicker if you have the first few perfect cubes memorized inside of your head. So if you haven't already, try to get those down. Let's do the cube root of 54. So the cube root of 54, if you look at it, you will probably be thinking of a 9 times 6, because that's one of the basic times table. But we don't see any three numbers repeated here, so we're going to keep breaking it down until we recognize three of the same numbers. So 3 times 3 is equal to 9, and then 6 can be broken down into 2 times 3. So we see here that 3 is repeated here 3 times, so we can take that out, and then we're left with 3 times the cube root of 2 as our final answer. Another way you can approach this problem is that 54 can be broken down into 27 times 2, and from our perfect cubes we know that 27 is equal to 3 cubed. But in reality, not a lot of people know off the top of their head that 27 times 2 is equal to 54. We usually think of 9 times 6 for the most part, so this is a way to do it that way. But there's always different ways to solve the same problem. Next we have the cube root of 640. Now this number might seem really intimidating at first because it's a big number in the 600s, but if you just look at it, we see 4 with an extra 0. And we know that 64 is 8 times 8. So we're going to use that knowledge, and we can assume that this is 8 times 8 times 10 because there is a 0 at the end. So we're going to break down. Well, actually we don't even need to break down because since 8 times is 64, if you look back at our perfect cubes, we know 64 is 4 cubed. But we can also take the long way and break these all down just so that you guys can get the grasp of the concept. So I'm going to be doing just that. So 8 can be broken, both of the 8s can be broken down into 2 times 2 times 2, or 4 times 2 if you look at it, and 2 times 2 times 2 times 10. And we already went over that 10 cannot be broken down any further to get out of the cube root. So of 2 here that have 3 2's in it, sorry, that was really confusing. So that means we can take out a 4. So it's going to be 4 cube root of 10. Now we're going to work with some variables. We didn't do this with square roots, so it can be a little bit confusing at first, but in my opinion, it's also easier to work with variables than real numbers because you can see the exponents clearly. So let's dive right into it. I'm going to give you the cube root of 48, x to the 4th, y squared, z to the 8th. Okay, this can look a little bit intimidating or daunting at first, but once you break it down, it's really not that hard after all. So 48 is 8 times 6. We just know that from our times table. And then I'm going to write the rest down again. So by now we know that 8 is equivalent to 2 cubed. So I'm going to write that in. Now, since everything is simplified down into its exponents, all we need to do is focus on the exponents. This is how I do it. Because it's a cube root, you need to look at the exponents to see if there are at least 3 to be taken out. So what I mean by this is if you look at 2 cubed, there's exactly 3, so you just take out the base. So that's going to look like, let's put this over here, that's going to look, we're going to have 2 outside of the radical. And then 6 stays inside of the radical because it doesn't have any factors that are repeated 3 times. And then x to the 4th, we're going to do the same thing. We look at the exponent, and there is at least 3. In fact, even to take out x cubed. And so, because this is a cube root, and so because there's only one pair of 3, we just take out 1x. And then x to the power of 1 is left behind. So you do the exponent minus the index. So 4 minus 3, so x to the power of 1 stays inside of the radical. Y squared, on the other hand, also doesn't have enough to be taken out. And then z to the 8th. So there's more, you can take out more than just one group of 3. You can actually take out 2 because 8 is greater than 6. So if we take out 2 groups, then that means we're taking out 6, and 8 minus 6 is equal to 2. So that means that 2 to the second, or z squared, is going to stay inside the radical. So our final product is going to look like 2x and then z squared, because we took out two groups of 3. And then we're going to have the rest of the cube root, which is 6x and then z to the square. Next, we're going to do a similar problem, and I'll try to write smaller this time so it's more clear. So we're going to do the same thing. We're going to simplify everything down into its exponents first. And then we see here that, sorry, this looks like a z, but it's supposed to be a 2. So 2 has 3, so we can take 3, so we can take that out. And then y has more than 3, so 4 minus 3 is equal to 1, so inside the radical. That one was really easy. I probably should have done this one first, sorry. And then next we have the cube root of negative 56, x to the 4th, and y to the 5th. So we're going to simplify down 56 first, which is 9 times 6. Sorry, not 9 times 6, it's hello? Okay, sorry, my connection cut out. So, negative 56, we know from our times table is 8 times 7. So, we know that 8 is 2 to the 3rd, and then we have 7, which is a prime number. So, we take out all of the numbers with an exponent of at least 3. So, we're going to take out negative 2, and then we take out x, and we also take out y. And now we think about what's left over. 7 wasn't taken out, and x to the power of 1 wasn't taken out, and y to the power of 2 wasn't taken out. And that's our final answer. Next, we're going to do some multiplication. I'm just combining all sorts of problems in here. So we have the cube root of 16x squared times the cube root of 81x. So the first thing we want to do is simplify these factors to make it easier to multiply. So 16 is 8 times 2, which we know is 2 cubed. And then 81 is 9 times 9, which we know is 3 times 3 times 3. So we're going to take out the 2 from here, and then we're going to be taking out 3 from here. So now we're free to multiply. So just like square roots, we multiply whatever's in front first, which is 2 times 3, and we get 6. And then we multiply everything inside the radical. So 2 times 3 is 6, and then x squared times x is x to the power of 3. And what do we know? We have a variable inside of the radical that can still be taken out of the cube root. So we get 6x is equal to that. Now we're going to be simplifying. Let's do something a little bit easier. So we have x to the 4th and y to the 6th. So we can both of these exponents are greater than 3, so we know we can take out something for each variable. So we have an x to the 3rd that can be taken out, and then we also have a y to the 3rd that can be taken out twice, because 6 is 3 plus 3. So all that's left is just x. Let's do another multiplication problem. We have the cube root of 4 times the cube root of 80. So 4 is just 2 times 2, so there's nothing that can be taken out of the cube root. But 80 is 8 times 10, and we know that 8 is 2 cubed, so we can take out a 2 and we leave in the 10. So now we multiply everything in front of the radical, and we just have 2 here. And then we do 4 times 10, which is 40. And if we think about this, 40 is 10 times 4. And I feel like we might be able to work with something here, so I'm going to simplify this into 4 times 10, and we know that is 2 times 2 times 2 times 5, and look what we know. 2 is repeated 3 times, so we can take out another 2, multiply it with what's already there, so we get 4. That's our final answer. Now I have a few problems with dividing with cube roots. And this might be a little hard to explain, so bear with me. But let's start with our first problem. Let's take it a little easy and work with some perfect cubes for our first problem. So I have y cubed over 125. And we know from square roots that you can just split up the radicand into both the numerator and the denominator. And since these are both perfect cubes, you can just take out the y, and 125 is 5 cubed, so you just take out the 5. So our final answer is y over 5. Next, we have one over the cube of 25. So what's wrong with this is that there's a radical in the denominator. I briefly talked about this in a square root video, but you always need to rationalize the denominator, which means that only the numerator can have radicals, if any. So first we're going to simplify 25 into 5 squared. So we see here that we need one more 5 to be able to take the 5s out of the cube root. So we're going to multiply by 1 essentially. If we do the cube root of 5 on both the numerator and the denominator. So by multiplying these two together, we're going to have 5 cubed inside of the cube root, which will essentially get rid of it. So now we have this after the multiplication, and we can simplify the denominator because 5 cubed has enough 5s to be taken out of the cube root, so we take out the 5, and you have a rationalized denominator. Our next problem is going to be similar. We have cube root of 9 over 49x squared. So the first thing I'm going to do is split these up into the numerator and the denominator. Now we're going to simplify whatever's the numbers inside of the cube root. So this is 3 squared. It's easier to work with exponents because you can clearly see how many more of what number you need to take it out of the cube root. So that's our simplified version, and since we want to rationalize the denominator, we look at the denominator and we see that we have a 7 squared and an x squared. And neither of them can be taken out of the cube root because there's only 2 for the exponent and not 3. And to get 3, obviously we just need one more of that factor, so we need one more 7 and one more x. So we're going to be multiplying both the numerator and denominator by just that. And I mentioned this in another video, but the reason why you need to do it to both the denominator and the numerator is because you don't want to change the whole problem. If you have the same number on both the top and bottom, it's essentially equal to 1, and anything times 1 is equal to itself. So we're not really changing anything by doing this. We're just rationalizing the denominator. So we have the multiplication, and so now we just need to carry it out. So looking at the numerator first, we do 3 squared times 7x, which is just 9 times 7. And we know that 9 times 7 is equal to 63, and then we have the x. And then for the bottom, we have 7 cubed. We have 7 cubed and then x cubed if you do the multiplication. So we're just left with 7x if you take it out of the cube root. And so this is our final answer with the denominator rationalized. Now let's try the cube root of 3 over x squared times y. So we're going to split the numerator and the denominator into their own radicals to make this a little easier. And because we need to rationalize the denominator, we see that it needs another x and 2 more y's. And so we're going to be multiplying by x times y squared. And if you do this, for the numerator, we get 3 times x times y squared, which is just 3xy squared. And then for the denominator, we get x cubed and y cubed. And so we can take those out of the denominator in the cube root, because now there's 3 of each of them, so we just get x times y for the bottom. And that's our final answer. And even though you can rationalize the numerator, that's going to essentially give a radical back to the denominator. But in the numerator, radicals are allowed. In the denominator, radicals are not allowed if you want a rational number. So this is why we go through this